Hi everyone, my name is Xiao Mi. It's introduced yesterday. I'm a research scientist at Google. I'm part of the hardware lab in our office in Santa Barbara. So today I'll be talking about, I know this is a bit different than what we put on the website, but I'll be talking about two works which have a very common theme of thinking about how to protect quantum information using many-body states. Before I go into the details of the work, let me first, recap what I talked about yesterday, which is the three axes of our next program. Going from in-depth understanding of the computational complexity of noisy observables to new quantum control and what we can do with these things to discovering new things using near-term experiments. In fact, there are three talks from our group which actually cover these three areas nicely. So right after me, Kostya here is going to talk about the first block. Trond Andersen is going to talk about the second block, and my work sort of touches upon the third axis. So as I mentioned, there are two main works that will be covered through this presentation. They all came up in the last year or two. The first one is called Noise-Resilient Edge Modes on a Chain of Superconducting Qubits, and the second one is called Stable Quantum Correlated Many-Body States through Engineered Dissipation. So as I said, both of these have a common theme. They were all motivated by us thinking, how can we, or is it possible to protect quantum information using many-body states that we can create on these noisy NISQ type of devices? The answer to the question certainly is yes. Otherwise, I wouldn't have asked it. So one very famous example of this is the idea of using topological edge modes to do quantum computing, and this has an example of this Majorana edge modes, which if you have a chain of fermions, the Majorana operators, they get paired through the bulk of the chain, but then on the edges of this chain, there's this unpaired Majorana operators. And if you think about the level spectrum of the system, then you would end up with a pair of degenerate ground states separated from the bulk energy spectrum by a topological energy gap, right? And if you have a fermionic system at your hand, then one can sort of engineer Pauli operators using these Majorana operators living on the ends of this chain. And the nice thing about this, at least conceptually, is that these Pauli operators, they have Majorana operators separated in space, and local noise is typically not strong enough to destroy these operators. So this is very nice conceptually, but of course we know practically it's very hard to do these systems or find these systems in nature. One can try to, let's say, do a spin orbit coupled nanowire chain, but it's very the signature of these things are usually quite murky. So when we thought about this, this problem, we thought, okay, can we encode such a Hamiltonian onto a quantum processor? The answer is again yes, although you do have to pay quite a bit of the cost in terms of doing this. So the idea is, okay, let's take the fermionic chain and then do a Jordan-Wigner transformation and map them into spin 1/2 operators. So what this sort of edge mode operators become is it's a sum of different Paulis, right? Going from single body terms all the way to many body terms, and the weights on these Paulis tend to shrink as the size of the Pauli grows. This mapping is effectively destroys the local nature of these Majorana edge modes, and which leads you to believe that they will be sensitive to local noise. So this is cost number one that you have to pay. The cost two that you have to pay is with noisy devices, we are typically limited to the circuit depths we can potentially run. So trotterizing actual, let's say, transverse Ising model is very difficult. So what we usually end up doing is doing some form of a kicked Ising model. So basically a heavily Floquet version of that. So the circuit diagram is showing here. So you effectively do a periodic circuit, which each layer has a layer of these X rotations with some power G. So these are usually somewhere between, for this work, it's typically between 0.5 to 1. And then you do a layer of ZZ interactions, right? So one can think of this as a trotter step of the transverse Ising model. But in this framework, we think about it more or less as a Floquet system because these angles are rather large. And then what you can also do is insert a layer of Z-gates that break integrability and just to see what happens to the observables. Now, since now we're dealing with Fouquet system, there's a second cost, which is the fact that there's no, I mean, the quasi-energies lie on a circle, or the quasi-energy states lie on a circle. There's no ground state per se, right? There's no notion of up or down in energy, which means that your qubits, which are subject to T1 decay, are not immune from that noise. T1 will basically take you all over the place, cause heating in this spectrum. You already told you two things that are bad. One sort of almost asks, why would you bother to do this? Well, there's still something in this model after the mapping, which is Z2 symmetry, right? So Z2 parity symmetry. The model has this particular symmetry. What this leads to is an interesting pairing of the quasi-energy states in the eigenspectrum of the Fouquet system. So if you think about these states on a circle, there's a pairing. So any state you can point to has a diametrically opposite state, which is usually separated by a quasi-energy of pi. So the question we want to seek to answer is what this pairing gives you in terms of stability and, let's say, protection against noise. Okay, so let's just go straight into data. So here is a chain of 47 qubits, pretty long. And the first thing you would look for is what happens to local observables. So what we're doing is we run this dynamics, starting from some sort of random bit string state and just let it evolve for a very long time. So this is up to 300 cycles. And immediately you notice something quite striking in the sense that the observables, these local Z polarizations, tend to vanish throughout the bulk of this chain. So this is a log scale plot. So the first cycles are kind of rather big and then become smaller. But nevertheless, you can see everything vanishes in the middle of the chain. But on the edges, there are these kind of oscillations which are sort of zoomed in here that live on over 300 cycles, and is still kind of going. If you're patient enough, you can keep measuring them. And then, in the bulk, everything basically disappears after 10 or 20 cycles. So this is an immediate signature. There's something, interesting going on the edges despite all these crazy mappings. In fact, if you zoom in and if you actually sort of fit the decay envelope to some sort of a time constant, it's actually identical to our single qubit T1. When you look at it, what the heck, right? What happened to dephasing, or T2? So why are you supposed to see that? So this gives you some hope. Oh, well, maybe this system is somehow robust to dephasing processes, and this is what we want to understand better through the following experiments. Okay, so in this particular measurement, we broke integrability just to see how robust things are. So to understand things better, it's typically easier to start with the integrable limit and see what features of this model actually give you this protection. So what we did is we kind of killed all of the Z disorder in the model, and then start to look at smaller system sizes. So this is 3 different system sizes going from 6 to 18. When the system size is small enough, what you can do is a bit of a spectroscopic measurements. So what you can do is simply measure Z as a function of time, and then change the control parameter, which is this X rotation G. And then for each value of G, you can do a Fourier transform of this time dynamics and get a Fourier spectrum out. And then this is the actual experimental data showing how the Fourier spectrum for different values of G. Here you immediately notice something interesting in the sense that because this is now a free fermion system, there are really just 18 sort of N or L single particle bands, and you can see them immediately in the data. But then there's one particular band that behaves very differently from the rest of the chain. So that's this bright band in the middle. So you can see that when the G is very close to 0.5, this is where there's a phase transition in the model, and the system goes from a gapped model to a non-gapped model. So you can see as you move away from this critical point, a gap opens up between this central mode to the rest of the system, and then there's start to have a degeneracy, right? So the two modes actually split when it's close to the phase transition, and then merges into a single mode as it goes along this control parameter. And the same thing is observed for larger system sizes. So what does this mean in terms of noise protection? Well, what it means is that you actually now have a very stable quasi-energy, right? So yeah, this is just another illustration of that effect, right? So you can see that as I change the system size for a fixed value of G, the sort of the quasi-energy gap, sorry, the degeneracy start to show up, and the energy difference between these two degenerate modes start to become pi, more or less. So this basically tells you that there's a quasi-energy gap, pi, which asymptotes to a value of pi as you increase the system size, and get goes away from a critical point of the model. So the question is this quasi-energy gap stable against noise perturbations? And to understand that, it's actually better to compare this against another particular model where you will see similar behaviors, but a different type of symmetry. So we, as a point of comparison, we run basically a Floquet version of the XY model. So here is effectively, running squared isop gates, one layer after another, and each layer we insert some sort of disorder. And here you actually see that on the edges of the chain, you also notice, these XY correlators that oscillates very much like the Marana edge modes, right? But the system crucially has no symmetry. So now let's compare these two types of edge modes in terms of their noise resilience. Sorry, before I go into that, let me also kind of show this energy spectrum of this particular XY model edge mode. You can see here that, again, you have a lot of these bulk energy modes that you can see on the device. And then there's a central bright edge mode that changes with the control parameter. Here is some phase in the squared isop gate. So even here, you can notice that this energy is always first order sensitive to the control parameter, this isop phase. So there's nowhere on this plot where you would have a sweet spot, right? And this has a fairly sort of dramatic implication in terms of the response of these two models to perturbations in the Floquet parameter. So how do we probe that effect? So one thing you can do to probe the effect of dephasing is to do disorder averaging. So what you do is you introduce disorder, this disorder into the model, and then you average over ensemble of this disorder and see how this affects your local observables. As you do this process, you notice the response to this disorder averaging is quite different between the two models. In the case of the XY edge mode, things just go all over the place, right? So these two plots on the left, the top plot is what happens to this XY observables as you change the disorder realization. So each instance pretty much give you a different beating. And when you average over them, you see a fast decaying observable. And then in the middle here, we're doing the same thing to the Marana mode, what's in this transparentizing model. And you see that pretty much the observable is insensitive to the disorder introduced. And of course, doing disorder averaging doesn't change the decay constant. And these little panels here just shows that how fast the height of this quasi-energy peak vanishes as you crank up the disorder strength. In case of XY model, things just decays exponentially and very quickly. In the case of the Marana edge modes, things are pretty constant or decay slowly. Yeah. So this little piece of work basically tells you that in fact for many body states, despite the noise that you already have in the device, they can really buy you something. If you do have a robust quantum phase, like what we have here, then the stability of this phase can give rise to certain passive protection against noise. Not against everything, only against T2. So now, after we completed this work, we talked to Dima and thought about, okay, this sucks, right? Our T1 is really short. Can we do something about that? So then we started to think, can we introduce additional ingredients into this caked icing model that allow us some degree of protection against T1 as well. So this motivated our next work, which is non-unitary dynamics. Of course, you can never protect against T1 if the whole dynamics is unitary, right? There's no magic there. You're just going to leak into the environment. But you do have a chance if conceptually you introduce some sort of non-unitary element into the quantum dynamics. And this is a time-honored field, right? So dating back probably decades. So the idea is if you have non-unitary dynamics, and the whole thing is typically described as some sort of Lindbladian. Here, in addition to the usual Hamiltonian evolution, you would have these jump operators that are acting on the density matrix. If the jump operator sort of commutes with the Hamiltonian, usually things are rather boring. Over time, let's say in the case of decay or dephasing, you sort of collapse into some boring state. But if the jump operators do not commute with the terms in the Hamiltonian, then something interesting can in principle arise. And this kind of so-called driven dissipative dynamics can lead to some steady state that hopefully have some entanglement or some interesting characteristics. So this is a generic framework, and of course, a lot of work has been done in this area, dating back to the days of optical pumping, to more recently in the context of qubits. People have engineered single qubit cooling so they can stabilize a single qubit state somewhere around the Bloch sphere and have it there forever. And this has been extended to qubit states as well. So you can sort of easily prepare Bell states using some sort of dissipative dynamics and have it stay there with some fidelity over very long times. Yeah. So all these are nice proof of principle that dissipative engineering can in principle give you a long-lasting state that goes well beyond the T1 of your qubits. So what are we trying to do? So now we have a big system. So the question becomes, what happens if you apply such a scheme to a very large quantum system? There, you're dealing with something a bit harder, right? Large quantum systems means the whole thing is much more sensitive to noise. There is a lot more noise. Can you still cool it? Can you still drive the system into a steady state that preserves some degree of entanglement? So these are the crucial questions that we're trying to answer with this second piece of work. But before I go into the circuits and talk about the results, let me first give an intuition of how one might conceptually thinking about cooling a many-body system. So the idea is, let's say you have a system which is this. You see my cursor here? Okay. So let's say you have a system which are have a lot of states, and let's say it started from a total mass, right? It's kind of somewhere in the higher states. Let's introduce an auxiliary system, which is, let's say, for this work, it's pretty much just a two-level system. It's cold. It's in its ground states. Now let's engineer some sort of hopping, some sort of interaction between this auxiliary system with a many-body system. So you have to do this interaction right. So this is something I have to emphasize before we go on further. It's not like any sort of interaction is going to cool a state, right? This interaction has a form that it removes quasi-particles or some sort of excitation from the system and then transfer it to the reservoir. So despite this innocent letter G, it's something usually complicated in practice. But luckily for the model we do, it's possible to find this operation. Okay, let's say it's possible. Then it transfers the excitation, some sort of heating into the reservoir and then kicks the reservoir into an excited state. So now let's do a non-unitary operation, which is reset. This is something nowadays we can do on our devices with quite high speed and high fidelity. And then that kills this excitation in the reservoir. And then you just keep this cycle going. So if you keep it going, of course, then the system is going to cool, right? It's going to drop toward the ground state. But still, there's noise in the system. So this noise is going to keep heating it up, right? There's an up conversion rate, gamma S. And so after some transient time, you expect the competing effect of cooling from the reservoir and the heating from the noise is going to bring the system to some steady state. And we want to ask, as the system becomes really big, what is this steady state? Is there any non-classical characteristic of it? Does it actually resemble the ground state or low temperature state of the model? Okay, so again, the model we studied in this system is a good old transverse field Ising model. Here we're not doing the kicked version of it, so we tend to keep this control parameter G small here. So this really emulates a trottlerized version of the Ising model. So here it's good to, again, look at the phase diagram of the model. So we have two well-known phases, right? In the limit where the x-axis interaction is much bigger than z, you have effectively an antiferromagnetic state, where the ground state has twofold degeneracy, is some sort of GHZ-like state. And as you tune across the phase transition where G exceeds the magnitude of J, then you go into some paramagnetic state, which is where the ground state is sort of like a product state. Yeah. Why do we choose this? Well, it's easy to do for one, but also the ground state actually has entanglement, particularly at the critical point. So it's a nice benchmark for us to figure out whether this sort of dissipative dynamics can give a rise to an entangled many-body state. Okay. Now let's again start with 6 qubits and just get some intuition of how this works. So this is the quantum circuit that we, periodic quantum circuit that we use to cool the transverse field Ising model. It's a bit more complicated than what I showed you in the previous work because now you have this reservoir. So let's walk through different blocks of this circuit carefully. So within each cycle, what we do is a Trotter step. So this U is pretty much just the Trotter step for the transverse Ising model. So nothing special there. And then we have this auxiliary system of qubits. These are kind of driven by a phase gate, a Z gate to some power H. What is this H, right? Physically, it corresponds to the energy splitting of the reservoir. After all, you have to match the energy gap of the reservoir to some sort of many-body energy gap in the system in order to cool it. So the parameter H here effectively controls the splitting of the reservoir. Okay? And then what you do is you bring these two systems together and do a bunch of interaction between them. These are these so-called partial iswap gate. Why partial iswap? This is because, if you think in the fermionic land, this partial iswap gate actually corresponds to some operation that sort of annihilates a quasi-particle in the system and then creates excitation in the reservoir. Yeah? And then after every 4 cycles, you kind of kill it. So why after every 4 cycles and don't do it every cycle? It's because there's a detailed balance right here between how often you reset and how well you are removing energy. If you reset it too often, the quantum zero effect leaves you pretty much in the ground state of everything. So it's kind of boring. So this is why we settled on this particular frequency of 4 cycles. But that's not the only optimization we do. There are 2 additional optimizations, which is the magnitude of H. So you have to match the split, the energy gap, and then the amount of interaction you do between the system and the reservoir. So this is the angle for this partial iswap gate. So the reason for controlling theta is because if you interact too weakly, of course the cooling is highly inefficient, right? You're not removing things at a fast rate, a rate fast enough to combat all the environmental decoherence. Now, if you let it interact too strongly, then the energy level in the bath start to address the energy spectrum of the system, and then you don't cool into some state of the system. So you basically now expect that as a function of these 2 optimization parameters, theta and H, there should be a point where a cooling is maximal or optimal under our current noise conditions. And this is something we did experimentally where we swept these 2 parameters. And what we are plotting here as a color is the ratio of the final energy, steady state energy, as over the ground state energy of the 6-side Ising chain. And you see that, blue basically means you're closer to the ground state. And you do see that there's a minima somewhere here that denotes this is where you would get the best cooling performance. Okay. And then this is effectively a temporal plot of the cooling trajectory. So basically just to test how powerful this is, we actually scrambled the entire state at the beginning. So we run a bunch of random circuits and make it completely messed up. And then we see whether we can lead this messy state into something more ordered. And you do see that. You can see that the energy going from 0 sort of or the energy ratio went from 0 to something closer to 1. Of course, not exactly at 1 for this 6-side chain after a while. And then it just stays there. It doesn't change. Yeah. And then this inset shows the local correlators, right? The Z and XX. So these are the order parameters for the transverse Ising chain. You can see that at the beginning there's nothing there, and after a while, when the cooling is more or less reached a steady state, you can see that there's a XX and Z correlation showing up, and they nicely cross at the control parameter. Sorry, nicely cross at the critical point of the model, which is G over J equals to 1. Okay, so this is one way to characterize the system, is using correlators. But of course, we want to go deeper and ask ourselves, like, how well are we really doing in terms of fidelity? Yeah. So here, what you can do is, well, it's only 6 qubits, so you can do brute force tomography and get a density matrix and compare against the ground state of the model. In fact, you can do 2 things. You can either compare against the ground state of Hamiltonian, right, the transverse field Ising model, or you can compare against the vacuum state. I will define what that is in a minute, of the flow K unitary. right? So you can see that as you compare against flow K-unitary, which is this dashed line here, the fidelity is a little bit higher than what you would get compared against Hamiltonian. So this is actually an interesting thing where you can think about cooling even in the flow K picture, where a priori there's no ground state. Okay, and there's also another feature here, which is that when you're deep in the antiferromagnetic state, where you have a twofold degeneracy in the ground state, you see that fidelity, the overlap of the density matrix, the two low-lying states are almost the same. The blue and the red are the same. Basically, you kind of cool down to an equal mixture of the two states. As soon as you kind of go across the phase transition, this fidelity overlap, this state overlap starts to sort of split, and you have much bigger overlap with ground state compared to the first excited state. So this all intuitively makes sense, right? If there's no energy difference between the two ground states, you usually just cool down to a mixture of both. Okay, so now let's test, at least for the 6-qubit system, do we actually have any entanglement left, right? Just because you have some correlation function and some fidelity does not guarantee that you actually have entanglement. So what we measured here is, in the inset is a concurrence, right, which is a rigorous measure of mixed state entanglement in the 6-qubit chain. You can see that there's nothing at the beginning. After a while, once you're cold enough, the concurrence jumps up and reaches some steady state. It's not huge, but it's there. And same for fidelity. Nothing in the beginning, and then you reach some 50% or so of fidelity as time goes on. All right, so this is 6-qubit. As I said in the beginning, the motivation is really try to scale up the cooling and see where we get stopped. So let's first do 1D, and just make the chain much longer. So here it's going from 6 qubits all the way to 30 qubits. Notice that I scale up the system size. I also introduce more auxiliary or ancilla qubits to do the cooling, mainly because you have a lot more decoherence. It's longer chain, so you need more baths to take care of this heating. What's kind of nice here, if you look at just energy ratio as a function of control parameter G, the degradation is not too dramatic, right? So, it definitely degrades, but going from 6 to 30 qubits, where the system size is 5 times larger, let's say the energy density at the critical point only dropped from 0.75 to something like 0.65. So it's not a huge degradation. Would give you some comfort that this cooling scheme is at least somewhat scalable in the sense of you can maintain a fairly constant energy density as the chain gets bigger. But then the question is, how now can we want to look at fidelity rather than just energy density. How do we do that right now? Beyond 6 qubits cannot do tomography. So the approach we used is to actually think about the system as free fermions again. So there, the many-body spectrum is decomposable into single particle bands. So they're really just 18, sorry, I keep saying 18, I don't know why. They're really just energy levels there instead of 2 to the L, right? So all you need to do to figure out what the state is to measure the population of the state, the system in each one of these quasi-particle bands. And this, comes down to some ugly Pauli operators that you just have to measure on the device. But long story short, we measure that, and we looked at how these bands are actually populated. So this might look familiar compared to the previous work where we actually measure the energy of these bands, but here I'm actually measuring the population of each one of these bands as a function of a control parameter. So here the color, the data now is actually in the color, not in the curve. So the bright, population close to 0.5 means that this mode is barely cooled, it's fairly populated, fairly mixed, and something close to 0 means it's very cold mode. Here you notice something quite interesting in the sense that there's a gradient, right? As the mode energy goes larger, the cooling is more effective. This makes sense, right? Higher energy modes have higher momentum, they move faster through the chain, so they're more easily removed by the reservoir. Now there's this edge modes which pop up again here, and they're pretty mixed. And this again makes sense because these are fairly localized edge modes. Their momentum is almost 0, so they don't move. So these are notoriously hard to cool. Right, and then you can use this mode to kind of now compute what the state fidelity is. Right, you simply multiply the mode occupation number for all these bands and then get a fidelity out. But that's not all we want to do. We actually want to understand what does this state really look like, right? These are fairly populated, terrible, but fine. But how is the state actually distributed across the eigenspectrum? Namely, what is the dominant eigenvector of this fairly mixed density matrix? And here, one thing you can do is to do this idea of purification. So it's a numerical technique where it allows you to project the density matrix, experimental density matrix, to the the closest pure state. So one can do that and then figure out what happened to all these mode populations. And then immediately you notice something quite pure, right? So as soon as you do purification, all of this mode population drop by orders of magnitude. What does this say about the state? It just simply says that the dominant eigenvector, despite this is a terribly mixed state, the dominant eigenvector has a very large overlap with the vacuum state of the flow K-unitary. This is exactly what we hope to see. Nowadays, I mean, the systems are noisy, so we don't expect things to be very pure. But what we hope is to see a distribution where the system is largely thermal. And this just tells you that as the system improves, this protocol will give you a better and better ground state. And then, okay, just to make yourself feel better, now you can actually compute the state fidelity using this purified density matrix. And here you see something quite massive in the sense that even for 18-qubit transverse Ising model, you get a ground state fidelity of 86% after purification. I have to emphasize this is not the whole point of the exercise. I mean, these numbers are kind of arbitrary. But the point of this exercise is really to identify that the dominant eigenvector of the mixed state is actually the ground state of the system. Okay, and then you can look at other things like long-range correlations and blah, blah, blah in the system using this purified density matrix. They all look great. All right. So let me just move toward the end of this talk where I will show you two potential applications of these engineered reservoirs. Everything I've shown you in the second part of the work so far has been integrable, right? It's just a transverse field Ising model. What we want to do is really break integrability and see what we can get out of these engineered dissipative reservoirs. So one thing one can do is to try to use this to prepare a 2D state. Of course, preparing sort of for magnetic order state is very important for a lot of reasons, and this has been done a lot in other platforms. So doing this is just useful to compare what we can do on our platform against other systems. In fact, Trond Andersen will show you something else, some other way to prepare these states tomorrow. Okay, so let's apply to, and the other reason for doing 2D is integrable systems are rather easy to think about. There are well-defined quasi-particles. You know exactly what they are, whereas these things are much more complicated in a 2D setting. So it's actually not a priori clear that applying the same protocol to the integrable system will guarantee a cooling performance in 2D. So this is the second question we want to answer. So now we actually, really blow up the system size, went to 40-something qubits, where part of it is reservoirs, these orange dots, and then much of it is it's a system. So now we apply the exact same thing to the system. We optimize all the energy all the swap angle and all that, and we see that you actually still get cooling, right? Not great, but starting from zero energy, you get some energy density which is low. So if you go into the close to the paramagnetic state, usually you get better cooling performance. So this is kind of nice to see in the sense that something you learn from integrable model actually applies to non-integrable model in terms of removing excitations. And then this final state has some level of magnetic order, which a correlation length, which is not that long, but it's there. And then you can look at other things just to distinguish these final states from simple product states, things like Rene mutual information. You can look at pairwise mutual information, and you can see a little bit of long-range correlation. It's not great, but it extends beyond a few qubits. And then you can also look at mutual information between different 5-qubit patches, and they retain some sort of finite amplitude, even when they're sometimes not exactly adjacent to each other. So this gives you at least some sense that these states are in principle non-classical, that they're not really just product states, right? Okay. So the last thing I'll talk about is to actually apply the engineered, dissipative reservoir to do something else rather than cooling. What can we do with these things? Well, we can do transport, right? I mean, one can think about these things are effectively as sources and drains in a wire or something like that. And we can do models other than transverse Ising, let's say the XXE model. So what we decided to do is just study a boundary-driven version of the XX chain. This, of course, has a celebrated history by now. There's a lot of work, usually in the so-called linear response regime, looking at the transport characteristics of this model and see what it looks like. So, there's quite a few recent publications where there's a bit of debate about whether it's KPZ or non-KPZ and all that. But all of this are unitary dynamics in the sense that the setting is typically you prepare the system in some spin balanced state and you lift the barrier at some time and let it go, right? So what happens usually here is the characteristic of transport vanishes over time. After some time, the system equilibrates and there's nothing there to see. So what we want to maintain is some sort of perpetual motion through this wire and see what happens in long time scales. So here we emulate this Fouquet version of the XX model. So basically just driving this system with fsim gates one after another. On the boundaries, we actually couple them to qubits that are maintained at 0 and 1 state. So you can see that this X gate kicks this particular qubit to that 1 state after each reset. And then first thing we measure again is just populations. We look at how local Z changes as a function of qubit distance, so this horizontal axis, and time, which is D. So here you can see that in the regime where the XX interaction is much larger than ZZ, you have ballistic transport, even in the presence of noise. You can see this, there's a propagation of light cone that goes all the way from left to right. I think there are 26 qubits here. Whereas if you make ZZ much larger than XY, then this transport becomes diffusive. It goes a little bit into the chain, but then gets stopped. And this is the reason being that these things tend to form a very heavy bound state. And after a while, the phase velocity is so slow, the group velocity is so slow that nothing moves. So all these are kind of expected. What's kind of unexpected is if you look at how current decays as a function of time at the beginning, right? After a while, this current profile gets polluted by noise. But in the beginning, if you look at current as a function of time, there's a nice exponential. Usually what people do is to fit this exponent and try to figure out whether it's diffusive or ballistic or whatnot. So again, here in the limit of XX much bigger than ZZ or the other way around, we see ballistic transport where this is a constant or close to a constant, and diffusive transport where the exponent is -1. What's kind of interesting is in the estropic point where XX and YY is equal to ZZ, you have a exponent of -2/3. So this is something called a subdiffusive transport, which actually is a different form than what people observe in this linear response regimes, where it's typically an exponent of -1/3. So that's quite distinct. So this is an example where we kind of didn't know such things actually existed, but actually when we did it, we found, oh, well, this well-known model actually responds differently if you drive it strongly on the boundary compared to focusing on the linear response regime. Oh, I'm right on time, so that's it. Any questions?
Thank you very much for a great talk. Questions? There's the cube somewhere. Can you throw it? That's a mic. That's also fine for people.
Sector from a nice talk. I guess maybe I missed it. So if you engineer like a dissipative dynamics to like sort of stabilize the Hamiltonian model, like do you expect the dissipative dynamics at a finite time to capture the critical behavior of if you are crossing a phase transition? Like I think you have a plot where you are tuning the parameter, like maybe for the first part of your talk. Thanks.
It really depends on the model you're implementing. As I mentioned, we choose transverse Ising is because the quasi-particles are more understood, at least in 1D. So you can engineer operators that are quite precisely removing excitations and adding them. For generic models, things with long range in particular, these kind of vast system interactions tend to be quite complicated. And in practice, if you hit it exactly, I would expect it to basically cool no matter where you are. But in practice, usually you have some overlap with that desired operator, but then some other junk. So then there's a competition of heating from that junk and cooling from this overlap. And it's hard to tell what would happen at the quantum phase transition. Yeah.
Okay, over there.
Thanks for a nice talk. So usually we think of a bath as, have to be big and continuous. But here you're using a qubit. So could you comment on what makes these qubits great as a cooling device?
Yeah, so a continuous bath is definitely the best, but then in practice, it's also more complicated. We have thought about how to, even 4 levels, it becomes a little murky exactly what is a bath system interaction one should do to get the maximum cooling. It's just a complicated theoretical question. If someone can figure out how to do it with a continuous bath, I'm all ears. Just 2-level system is just easy to engineer. Yeah.
One last question while you're setting up.
I actually have 2 questions. Is that okay?
Just go for one.
Okay. So, I'll ask the simpler one. So very beautiful results. So you mentioned that it's, I mean, obviously it's a competition between noise and cooling.
Correct.
Like heating and cooling. So something I was missing is understanding what exactly the sources of heating are. I mean, of course, you guys characterize your errors and such very carefully. Mm-hmm. But do you have a sense of this? And then does the kind of knowing the noise really change dramatically the types of phases that are created?
Yeah, I understand. Again, depends heavily on the model. So, I mean, we know our noise, right? T1, T2, some crosstalk and whatnot. Yeah, you can sort of engineer maybe the bath system operator. If you know one noise is more dominant, maybe you can engineer the operator to particularly deal with that sort of noise. That's a possibility, but for transprecizing, yeah, we haven't thought about how to fine-tune things to optimize against one particular noise. Yeah, it's sort of more of a generic approach at the moment.
All right, let's thank Xiao once again.